In Chapter 3, Notes E, we're going to talk about the transition metals. We're going to go over some specific properties that are unique just to these transition metals. And so that we can go into some more detail, we're going to focus on only the first row, these first 10 specific elements. Keep in mind, though, whatever patterns we discuss in the top row will probably apply to the counterparts below. For example, if I talk about zinc, the properties for zinc will probably apply to some of the elements down below. We're going to focus specifically on these first 10 transition metals so that we can be very specific when we talk about their electron configurations and things like that. Here we can take a peek at what some of these transition metals look like in real life. Notice that they are metals, and so you see some typical properties of metals. We see luster, we see that they come in small filings or turnings, some shavings. We see one standout as far as color goes with the copper, which is more of a reddish color, but most of them are more of this like silver shiny color that you would expect metals to be. So these are our 10 transition metals we're going to be studying in Notes E. In order to understand some of the special properties that transition metals have, we have to understand their electron configurations. The stability associated with certain fills or half fills of these orbitals is going to be what drives some of the properties. So saying that we would start at argon, of course, for all of them, when we move on to our first one, we see that we've filled the 4s orbital, and then there's one electron in the d block. So the d block is where we start our transition metals. And of course, it's 3d coming out of 4s. So 4s, 3d1 would be our first transition metal, and then we fill that d block halfway when we reach the manganese and all the way when we reach the zinc. So this would be our different electron configurations for our 10 transition metals. Let's take a second to think about what this would look like in terms of an orbital diagram. So leaving off at argon, as you come across the potassium and calcium, your 4s, you're going to fill 1 electron, 2 electrons to fill your 4s orbital. That's going to bring you all the way up to calcium's electron configuration or diagram. Then as you start to fill for the transition metals, you're going to fill one at a time as you go across. So our first transition metal, then the second, third, fourth, fifth. So here at manganese, we have a perfectly paramagnetic 3d orbital. There is a stability associated with that. Then as you filled the 6th atom, we would add back to the first d orbital and then pair as you come across 7, 8, 9, ending with zinc at 10, a perfectly filled 3d orbital. Again, that's especially stable as well. One other thing I want to point out while we're looking at this is electrons are always lost from the principal quantum number that is the highest number or the furthest out. So the 4s orbital is the valence shell, and that will be where I remove electrons first before I steal electrons from the d orbital. Here we have a table of all of the possible oxidation state as far as atoms that we have actually found. These are oxidation states that we know exist. Notice that every single transition metal has a possible oxidation state of +2. And there is a pattern where you're in the middle with the manganese, you have the most possible oxidation numbers of +7. And then towards the beginning or towards the end of the row, you have less oxidation possibilities. For example, zinc can only have the +2. That was actually one of the ones we memorized on Think, Snow, and Love. And although it is nice to have this table to refer back to, the ones that are highlighted and bolded here are the ones that are going to come up over and over again. So these are nice ones to know of off the top of your head. Although we learned that transition metals are basically anything that are located in the d block on the periodic table, there is actually a very specific definition for a transition metal. This is the definition right here. An element whose atoms have an incomplete d subshell, or the cation of that atom can have an incomplete d subshell. So the cation would be what's formed when you actually give off the electrons from the 4s orbital. So we would be looking at something that has an incomplete d orbital, thinking of the 5 orbitals within the 3d energy level. incomplete, meaning not completely full. So that would be half full with 5. Completely full would have all 10. And yes, there was the 4s orbital before here, but we could also form the cations. So we could be losing some of these electrons for the 4s. So transition metal definition is really just focused on this full 3d orbital, which is funny because there actually is an element out of the 10 we're looking at today that is technically in the D block, but absolutely does not fit this definition. What element is it? The answer is zinc. Zinc has a completely full d orbital. And can form is 2+. Those 2 electrons would be lost from the 4s orbital, again leaving a completely full d orbital. So neither the atom nor the cation can have an incomplete d shell. Therefore, zinc is not a transition metal. This is actually a very common question that appears on the IB test to discuss zinc and its inability to meet that transition metal definition. There are a total of 5 unique properties that we're going to discuss associated with transition metals, again focusing only on the first row. The first is the variable oxidation states. This is something we've already started looking at, and we're going to go over a little bit more in this video. And this video is video E1. I'm trying to split this up. Some of these ideas are easier than others, so I've made short videos for each one of these ideas. So formation of complex ions would be the next video, and it'll be labeled E2. Then magnetic behavior would be labeled video E3. And actually I have some fun YouTube videos that I usually post as well that I didn't make. So that will have some extra videos on magnets. If you want to get into some of the magnet behavior, it's actually really cool, especially if you're taking physics or have taken physics. And then video E4 will go over catalysts, and then colored complexes is actually notes F. So that's a whole nother big idea. I know this is a lot more videos than we usually do in a week, but I think breaking it up like this is going to make it a lot easier to get through and a lot easier for you to be able to go back to and review. Some of these ideas are a lot easier than others. Now let's dive into why these transition metals can have different oxidation states. Typically, when an atom loses a certain number of electrons, it's driven to lose a specific amount of electrons. Why do you think the transition metals might behave differently? Well, here we can see an idea of how much energy it might take in order to remove electrons from certain energy levels. This is the order of filling, Aufbau's principle. So as you can see circled here, we have the 4s energy level and the 3d energy level, or orbitals, I should say. And those 2 orbitals actually have very similar amounts of energy. So removing the electrons from the 4s energy level will take a very similar amount of energy as removing electrons from the 3d orbital. That is actually why it is easier, or able to even, form different oxidation states, because we could be removing electrons just as easily from the d orbital in the transition metals as we could from the 4s or valence shell. Don't let that confuse you though. Just because the 3d orbital has a similar amount of energy doesn't mean it's less energy. The 4s orbital was a little bit lower than that 3d orbital. And so when we actually lose electrons, we are still going to lose them from the s first, because 4 is the valence shell. My 4s electron will be lost before I dive into the 3d orbital. So here we see an example of copper forming a copper ion. Before we talk about the ion, I do want to point out there was the exception for copper. In order to get a completely full or stable d orbital, one of the s electrons was stolen. So the correct configuration for even just a normal copper atom is 4s1 3d10. Then, in order to form the copper +1 ion, the 4s electron is then removed. So that leaves a completely full 3d orbital. So for the copper ion, the configuration is argon 3d10. I think this graph does the best job at showing how a transition metal can have different oxidation numbers, but a regular atom like calcium has a set number of electrons that it wants to lose. So here we have the successive ionization energies graphed. And if you remember, that basically means this is the amount of energy to remove one electron, to remove the second electron, to remove the third, remove the fourth, and so on. So as you see more dots as you move forward, we are removing more and more electrons. And this graph goes all the way up to removing 7 total electrons. So the furthest dots here would be the 7th electron being removed, after having already removed 6 from that same atom. Successive ionization energies. First, let's look at a normal atom like calcium. So the electron configuration for calcium would just be argon and then 4s2. So removing the first 2 electrons, removing the 4s, would get down to the noble gas configuration of argon. So we see after that a giant jump in the ionization energy. In order to remove the 3rd electron from calcium, it would require significantly more energy. We're up here closer to 5,000 kilojoules per mole, where the second and first required less than 2,000. So big jump in ionization energy. And then we see a gradual increase from there, as we would be removing from P6, P5, P3, P2, and P1. So we're kind of stripping out of the p orbital as we have this mild incline here. The most notable thing about the calcium's successive ionization energies is this big jump in between the s orbital and the p orbital. That basically means it is easy to remove the first and second electrons, but difficult to remove any others. So since it's easy to remove the 2 electrons, that's what calcium will always do. Calcium will form a +2 ion. Calcium will resist forming the +3 ion because it would require so much more energy to remove the 3rd electron. So you're always just going to see calcium as +2. Now let's look at the graph focusing on titanium. The configuration for titanium's argon 4s2 3d2. So we have 2 electrons in the d orbital as well as the 2 electrons in the 4s orbital. So the first 2 electrons removed would still be from the 4s orbital. But notice how close in energy the next 2 electrons are. We still see that it's fairly easy to remove those electrons. You don't get the big jump until afterwards, where you're breaking into the argon configuration. Here's where you would be removing from your p orbital. So the big jump is where the cutoff is. So titanium can't have a +5, but it could easily lose 1, 2, 3, or 4 electrons. Those would be easy to remove. So you're going to get oxidation numbers of +2, +3, and +4. A question I get a lot is why not +1? Same thing with the calcium, why not +1? And I don't have a great answer for you. The only cation that I know of that really likes to be +1, aside from, of course, group 1, is copper. The best answer I have is that a half-fill s orbital isn't as stable as you think it would be. It's just not something that we typically come across in nature. So typically skip over +1. If you look back at our table that we had earlier, you would notice copper was the only one that had +1 as an option. Start with +2, and then whatever other possibilities are before the big jump would be your possible oxidation numbers. I have seen a question like this on the IB test, where it gives you the graph and asks you what the possible oxidation numbers are. In order to answer a question like that, what possible oxidation numbers could this red atom have? Typically won't tell you what atom it is, so you can't pull from memory. It'll just give you the graph. You're looking for the big jump. Wherever that big jump is, you know that your possible oxidation numbers are below that. So skipping +1, we see +2, +3, +4, but not +5. That is not an option. So you have to know where to stop based on the big jump. And last, we'll look at some common oxidation states, some patterns that you should be aware of. So first of all, every transition metal can have an oxidation number of +2, and that's because they're losing from that 4s orbital first and then getting into the d orbital. And that d orbital is where it gets complicated, where you have certain preferences based on stabilities. Iron comes up a lot. That's actually one of our demonstrations for this chapter. The complex ion demo is all about iron having a +2 or a +3 oxidation state. Another one you should know about is for the manganese ion, +4 is emphasized in the IB book. That's the one that they want you to know about. I think it's because it's kind of a difficult one to find stable, and so that's the manganese ions able to form that +4 pretty easily. But I actually think it's weird that they don't want you to know about the +7 state in a very, very, very common ion called permanganate. With the MnO4-, you actually get an oxidation state of +7 for the manganate. Speaking of common polyatomic ions, sometimes being part of a compound or a polyatomic ion can actually help an atom be more stable. So you're going to see sometimes that the abundance per se, like how common a certain oxidation state is, can actually depend on what it's attached to. So we're going to go through a few common compounds and ions and try to determine the oxidation number for the actual transition metal, which will be what we use for the Roman numeral, if you remember your ionic naming, when you name the compound. So the first one is the chromium chloride. So chloride actually, or chlorine, has a -1 charge, but there's 3 of them. To do oxidation states of a compound, we want them to completely cancel out or be neutral. So how do we cancel out -3? We would need an oxidation number for the chromium of +3. And we would write that as chromium 3 chloride with the 3 in the parentheses. For the next one for chromium, we have a dichromate ion. With the 7 having a -2 charge 7 times up to a -14, we want a -2 left over, so we need a total of +12. But we have 2 chromates, so that would actually need to be +6 each. The oxidation number is the per atom number, so that would be a +6 for that chromium. And we would use VI for the Roman numeral to be 6. Next we have Mn attached to just O2 as a neutral compound. So again, oxygen we know is -2. We have 2 of them, so we're up to a -4. We want it to be completely neutral, so the manganese would need to be a +4 in this case, which is the state that IB wants you to know about. So that's an IV, manganese 4 oxide. Common name for that is per. Two of the transition metals. So if we're going for +2, each one would have to have a +1. So the oxidation state for the copper there is +1. And we would just say copper 1 oxide for that compound. So anytime you assign oxidation numbers to compounds or polyatomic ions that contain transition metals, you would always start with the other guy. Start with whatever they're attached to. As you see here, a lot of them commonly attached to oxygen. You may also see them attached to other anions, typically, since metals make cations. Then using those known oxidation numbers of the other atoms, you can work backwards to determine the oxidation state for the transition metal. Whatever that transition metal is, or charge per atom, is going to go into the Roman numerals when you name that compound. That's going to wrap up the notes for the D block introduction and the covering of all of the variable oxidation states. So next look for video E2 to go over the formation of complex ions.